Okay, I think we're ready to go. It's a great pleasure today to have Vlatko Vedral here. Vlatko holds a superposition of positions in Singapore and also in Oxford. And I think today we've collapsed him to Oxford. He has done too much work to summarize for me in such a short time, but he's also written several nice books, and it's a great pleasure for us to have him here today. I'm also curious how this whiteboard sharing is going to work out. That is the first for Q+. And so, without further ado, Vlatko, thank you very much. Please start.
Maybe you see it there. Thanks a lot for inviting me to give this presentation. I have a camera. So as I understand from Daniel, we are pioneering a new way of doing this thing. Namely, I was sufficiently lazy to write any notes in advance and then talk over them. So we have a whiteboard, and please communicate back if the writing is too small or unclear or not loud enough, if you like. I also happen to have a live audience here of a few people, which means I may not necessarily be looking at the camera, and it may be, that may explain why I kind of look in a weird direction if you don't see me looking at you directly and addressing you. So the topic will be on temporal entanglement and its relation to thermodynamics, and thermodynamics will be understood in the sense of the basically exciting work that's done in non-equilibrium thermodynamics due to people like Jasinski and I think Tasaki on the quantum side of things. So I will try to explain what I mean by temporal entanglement, and then I will try to explain what this non-equilibrium work and free energy relation captures, and that's basically going to be the whole talk. I'm very happy if I'm interrupted at any point, and I understand that you have means on the other side to interrupt and send messages as well and send questions. So please feel free to do so. Let me spend a few words on motivation here as well. Whenever you talk, especially if you read the non-equilibrium thermodynamics literature, you will encounter certain notion of the error of time. And the error of time is then presented as something fundamentally irreversible that arises from the protocols that are considered there. Coming from quantum mechanics, obviously you may think, how do these people actually in thermodynamics get an irreversibility out of a microscopic theory like quantum mechanics, which is fully reversible? And obviously this is a long-standing question. And we don't have an answer to that. In fact, there are so many approaches that it's probably very difficult for me to talk generally about it. But certainly within the specific example that I will present, you will see exactly how quantum mechanics does not discriminate really between the past and the future in that sense. So there is no asymmetry in time, whereas Jasinski's relations are somehow sensitive to the initial and the final states, and actually this is probably the way that this difference will come about is probably the way, in my view, that all of these differences come into play, which is namely that you somehow restrict certain things in your operations, which then lead to irreversibility. So basically, obviously, if you allow everything in quantum mechanics and you allow unitary transformations or any initial states and any final state, then there is no irreversibility. But if you on top of it give certain restrictions, such as I'm only going to consider uncorrelated state at the beginning, then you've effectively put in an asymmetry in time by hand, because you're giving different initial condition to the final condition. And I think all of these errors of time are consequences of us putting it in, deliberately by somehow discriminating the past and the future. So it's really an interesting topic, and maybe you see an instance of that. I find it very interesting, and there's probably more to be said about it. and many people have talked about it. So let me clear up one misconception. I think the first person who clearly stated that, at least as far as I know, is Eddington, who has this very nice. He wrote very good popular books. Actually, I think his style is fantastic. And what he did is he said, whenever you introduce probabilities into physics, then basically you can argue for an arrow in time. Namely, you can argue that there is something different between the past and the future. And the example that he could then argue that probabilities are not fundamental in classical mechanics; they are only superficial. But quantum mechanically, of course, we know that randomness in measurements is already there, and it's very intuitively somehow suggestive that you should take this as your irreversibility. So Eddington had this great example, I think, where he said, imagine that I have, so I'm slightly digressing just to kind of motivate this as a whole discussion of irreversibility and quantum mechanics. And basically Eddington said, imagine that I have two bags, and one bag contains two black balls and one white ball, and the other one contains two white balls and one black ball. And now he says, imagine I give you one of these bags. I don't tell you which one it is. Presumably I randomly choose one of them. And you put your hand inside, and out comes a white ball. What would you calculate the probability is that you were handed this bag versus the probability that you were handed this bag here? And of course, the intuition tells you that if you got a white ball out here, it's more likely to have come out of the bag that contains two white balls and one black than vice versa. And obviously, there is a Bayesian, so to speak, method to work backwards. But I think anyone here with any common sense, and hopefully the physicists are basically in that bunch of people, will tell you that the ratio should be 2 to 1. So there is twice as many chances that it comes from this guy than from that guy. And if you normalize that into probabilities, then you would say, with probability 2/3, really, I had something like this, and then with the probability 1/3, I had this back. And now Eddington says, let's flip this around. And so he wants to demonstrate that whenever you have probabilities, they are really somehow sensitive to the temporal ordering. So Eddington says, imagine I flip this around, and imagine that I give you one of these two bags, namely this one, because we concluded that's the one with a high probability. Imagine I give you this bag with 2/3 probability. What is the probability that you will take out a white ball? And if this was, according to Eddington, genuinely time invertible, then the probability should be 1 to get a white ball. Because in the first experiment, we took the white ball out. That was probability 1, if you like, and then we worked backwards. Now I'm given this with 2/3 probability, and of course, again, anyone who has any basic training in probability will know that you won't get a unit probability to get a white ball. Namely, you will get 2/3 probabilities times 2/3 from here, and then plus 1/3 times 1/3 that you get a white ball if you get this guy, and this is certainly less than 1. Okay, so basically, Eddington says, here we go. Using conditional probabilities in the forward direction in time is not the same as going backwards, hence irreversibility. Okay, and the quantum version of Eddington was, and I think that starts to become a little bit more relevant to what we are doing. You can easily quantize this, and it's clear that by looking at these things as maybe beam splitters, which reflect and transmit 1/3, 2/3 probabilities, you can kind of come up with a quantum argument for this. But an even simpler version was given by Penrose. And so Penrose, at least this was his view maybe in one of the early books. I don't recall now exactly which book this was. But his example is the following. So at least 20 or 30 years ago, he held a very similar view to Eddington, that irreversibility comes from probabilities and fundamentally from quantum mechanics. So Penrose's example is, imagine I have a beam splitter, and imagine that I have something here that generates photons. And now I have two detectors as usual, one detector here and basically one detector over here. And sneakily, you include another detector here, which is one of those, they're not so easy to make, but we have to imagine something that's like a non-demolition measurement of the presence or absence of a photon here. So if this detector clicks, there is a photon that's whizzing by, but it's not really being detected as such. So you should probably think of electrons or something else being the subject here. Now Penrose says, imagine I ask myself the following question. If I get a click in this detector here, what is the probability that this detector here will also click? And of course, if this is a 50-50 beam split, the probability here will be 1/2. But now if you work backwards and you say, given that I had a click in this detector, what is the probability that this detector clicked? And you've got to say 100% because there's no way you can get a photon here unless there was one that came to the beam splitter in the first place. So he would say going backwards, the probability is 1. Going forwards, the probability is 1/2. Here we go, irreversibility in time. Both of these arguments, in my view, are wrong in the sense that measurements and hence probabilities are not really what's at the root of irreversibility. And I think what's at the root of irreversibility in both of these cases is that your initial conditions are different to your final conditions, and you're really putting irreversibility in by hand. So let me show you, and I think really this gets me to the topic of temporal entanglement, which I will approach simply from this perspective of making an initial and the final measurement, and then I will talk about correlations between the initial and the final measurement. And the way I will phrase this, it will make it clear that it's completely symmetric in time. So the point I'm going to be making in this first part is that making measurements in quantum mechanics, even though we believe that probabilities are there fundamentally and we cannot get rid of them, these measurements are not really the ones that give you any asymmetry as such. You can phrase quantum mechanics even only with measurements fully in a reversible way. And I think that it's really Aharonov and his colleagues who made this point even more strongly in their papers in the 60s. And you can phrase everything I said so far in this view as well. So basically, temporal entanglement is a notion that tries to say that the correlations that we get from two spin half, let's say, particles, which are spatially separated, but they exist in some entangled state. These can be completely, so you know, this is like position 1 and this is position 2, if you like. These can be completely mimicked by correlations that we get from measuring a single particle at two different instances in time. This was probably first, like I said, it probably sits somewhere there in Aharonov et al. Work, but I don't think that was exactly the point that they intended to make in the 60s. And I think it was for the first time really brought out by Leggett and Garg, who, for a different reason, had a different motivation to divide this inequality. And I'm going to completely remove myself from any philosophy behind this, and I just want to show you how the mathematics works, because that's going to be relevant for the thermodynamics later. So basically what Leggett and Garg said, in some sense, is that you can test the CHSH kind of inequality on a single qubit where the measurements are done at two different times but in the same spatial location. And that, in a way, will give you the same violation of Bell's inequalities as would two qubits that are separated in the usual CHSH scenario. And I think this is very interesting. So someone comes along to you and gives you statistics of two different types of measurements. And from the statistics that you get, you cannot tell whether these measurements come from a single system at two different times or from two different systems at the same time, if you like, whatever that means. So quantum mechanics is somehow blind to this. And to me, this suggests almost the opposite. So I think people like Asher Perez are well known for their great pragmatic attitude to quantum mechanics. And I think he certainly tried to rid it of any kind of metaphysical connotations. And he's well known for saying things like quantum objects don't live in Hilbert spaces, they live in space and time. I would almost say what this shows to me is the opposite, that quantum mechanics doesn't care about space and time, and it only lives in Hilbert spaces. And space and time are something we kind of choose to apply our quantum mechanics to, but in this view, they're only of secondary nature in some sense. I mean, I don't know, probably there is something more intelligent to be said along these lines, but you won't hear it in this talk. So anyway, let me just show you how this works, and it's really nice and simple. Another interesting thing that's going to come out of it is that you have to be careful. Here, in 2 qubits case, we always emphasize that states are entangled. And even though entanglement is seen in the correlations between 2 measurements that you make, we always emphasize that states are either entangled or disentangled. Here, of course, there are no states, because you can't write a quantum state across time, so to speak. So you know, you can write a quantum state x1, x2, and t, but you can't write a state x, t1, and t2. I know that people have tried, but we don't really have any intelligent way of doing anything like that. And yet, so we can't talk about temporal entanglement in the sense of states, but we can talk about temporal entanglement in the sense of correlations between measurements. And that's, of course, after all, everything we get anyway in quantum physics. So, so in that sense, it's already clear from what I'm saying that whatever the input state of your qubit will be here, before I make the measurements, will be immaterial. So temporal entanglement will have nothing to do with states of your qubits. In fact, it will be independent of it, and that's really an interesting thing, I think. Whereas here, of course, it's all to do with states in some sense. So let me phrase this in the following way. You would start with an ensemble of identically prepared qubits. So it's always the same. And then you make a decision to perform 2 different measurements in the first instance and 2 different measurements in the second instance. So, you know, to follow the CHSH notation, you could make a measurement of an observable A1 or A2 at the first instance, T1, or you can, and then you can measure B1 or B2 at the next instance. And then you can go down this ensemble and basically perform either of these 4 possible measurements on each of these qubits, and ultimately you get the average. So basically, if you want to make it really completely analogous to CHSH, at the first instance in time, you would toss a coin. If you get heads, you would measure A1. If you get tails, you would measure A2. Then you would wait for the system to evolve to T2. Then you would toss a coin again, and if you get heads, you do B1 and tails B2. And ultimately, you'd be writing down exactly the same correlation combination of these measurement outcomes, which is the usual one, and I think everyone here knows about it. And basically, you'd be, so each of these can have a value of plus or minus 1. And what you'd be doing ultimately is making an average over the whole ensemble where you randomly chose to measure one of these 4 possible combinations. And ultimately, if you have enough of these systems, then you would get a good enough average. And of course, now you have to be very careful, and that's why I said I don't want to go into any philosophy. At this point, you have to be careful to say what classical physics would give you this in this instance, and then you contrast that with quantum mechanics. But one thing is clear: quantum mechanics can achieve the maximum value of 2 square root 2 in this kind of combination of measurements. So the way you do that is that the choice of A1 and A2 would be like your Z measurement and your X projected measurement. And so the maximum violation comes from exactly the same combination of operators that you would measure if you were to maximally violate the CHSH on two separated qubits. And that's not an accident, like I said. This only confirms that quantum systems live in Hilbert spaces and not in space and time. So the other choice is exactly, z plus x over root 2 and z minus x or whatever, x minus z, I think, over root 2. And if you substituted these values here, what would come out quantum mechanically is the expectation value of xx plus zz. And to those of you who've kind of worked in these entanglement witnesses, this will immediately kind of ring a bell, because this is one of those entanglement witnesses for two qubits as well. So it's not really an accident that it looks exactly the same. Note that I've been completely careless to even label the temporal. So this now goes back to the point that the temporal asymmetry is simply not there. It really makes no difference which of these measurements I perform first and which one I perform second. I'm not even bothered about the evolution in between. It could be unitary, it could be identity, if you like. But the point is that these kind of correlations are completely blind to the order in which I executed my measurements. And from this form, you can also see why there is an independence of the initial state rho. So I don't even have to write. So first of all, I don't need to write the indices here, which one is done first and which one is done second. It's completely symmetric. Secondly, I don't need to write the reference state rho. It could be maximally mixed state. It could be pure superposition, whatever you like. And the point is that once I project onto x the first qubit, then the next measurement of x can only give exactly the same result. So you can see where the 100% correlation comes. Oh, sorry, I think I've omitted square root 2, which is very important, otherwise it wouldn't be quantum. So what I'm trying to say is that the average of xx is always 1 independently of the input state, and zz is likewise always 1, and this gives you the 2 root 2 that I wrote down before. So again, the message is the order doesn't matter. Once you make one of these projections, you can call it the future projection if you like. I mean, we find it very difficult to do things in the future before we do things in the past, but that could well be just our asymmetry, and it may not be part of natural order at all. Anyhow, once you measure the qubit in the state x and you repeat x, then obviously you will get 100% correlation. This is all this is telling you, and that's why you get 2 root 2. Now, of course, you can say, why do you claim that this is better than what can be done classically? And this gets us into all sorts of assumptions that you would put on classical theories. And I'm not going to do that because this could probably provoke an endless argument. When I wrote this paper with my two project students and with Czaslaw, we actually, in the end, didn't even publish it. I think we had so much hassle from the first set of referees that none of us really bothered to even pursue this any further. And I think most of it was really interpretational, which I think wasn't the point of that anyway. But one simple way of thinking what would classical physics tell you in this case is to imagine classical statistical mechanics, which means that your states are always diagonal in the same basis, and your measurements can only be done in that one basis. So classical physics doesn't have superpositions, if you like, in this sense. And that would mean that once you choose the z direction as your classical basis, then everything takes place only in the z direction. So you can see that in this kind of average, you can at best get number 2 out, and you follow exactly the logic that is followed in the usual Bell direction, namely that you write, A1, you factor it out, B1 plus B2, and then you've got A2, B1 minus B2, and then you look at the maximum classical value that this can have, and you can see that this can be at most 2, and the least value is minus 2. So basically, classically speaking, you get exactly the same upper bound as you would for 2 qubits, and then quantum mechanics gives you the same 2 root 2 value. And like I said, this is interesting. First of all, it's interesting that that correlations are blind to space and time. And secondly, it's interesting that they are completely time symmetric, and it doesn't matter which order we take. And I think now I want to switch to the other topic. So I don't know if I should.
Okay, so for those of you in the live stream, actually, Vlatko has just left, but I hope he will be back in a moment. So please hang on.
You have to apologize.
I'm sorry. I'm sorry.
Okay, back. You're back. I think.
So hello, I'm sorry that we had this interruption, which I hope came exactly at the punchline point of me concluding the temporal entanglement. If not, I can repeat whichever part you like me to repeat. And if everything is okay, I was just saying that I'd like to maybe make an allowance for questions now on this part, because I'm going to move on to the Jasinski bit in thermodynamics, and that may be slightly different.
Okay, so we can't actually see Vlatko at the moment. We see the audience of Vlatko.
Very good. So we have to switch to the other camera.
To the other camera. And if anyone has a question regarding the first part of the talk, temporal entanglement, please raise your hand or let us know when you need.
He might know how to switch to this.
So maybe I'll start with Janet Anders at UCL. Janet?
Yes, can you hear me?
Go ahead.
Can you hear me?
This is somebody's asking a question, I think.
Hello, yes, I'm here now. I'm just going to switch back. Hi, yeah.
Hi.
Hello.
Hi. Oh, right. Hi. It's me. I wanted to ask about the temporal entanglement. And I'm not familiar with it. Can you hear me?
Can you speak up a little bit?
Okay. I'm screaming. I'm not familiar with it, so you said that temporal entanglement also obeys a Valley inequality. And some I'm guessing now that some temporal evolutions will violate a bit of inequality maximally, and some won't. I was just wondering which temporal evolutions do the maximal violations.
I think you can phrase this actually in two equivalent ways, which may already capture what you are asking. So the way I phrased it is that I had no evolution between the initial and the final measurement. So I made the initial measurement in one of the two bases. Then basically all your evolution did is waited for a certain period of time. So the Hamiltonian was assumed to be 0, if you like. And then there was a choice between the other two measurements. If you want any evolution in between, and in fact this is how Leggett and Garg phrased their inequalities for some other reason actually, which was important to them. If you want this evolution, you can always incorporate that into final measurements. So remember, any evolution you have in between can simply be seen as a rotation of the final measurement basis. And if you rotate the final basis by exactly the same amount, U dagger U, so to speak, then you would get exactly the same maximum violation. So in other words, if you choose to evolve, then you would have to adjust the final measurements, which can always be adjusted to cancel out that evolution, and they still give you the maximum. So any evolution can give you maximum, in other words.
Any unitary.
Any unitary evolution. Sorry, I didn't speak about, you're absolutely right. There is so much to be said about this topic. You could do a kind of more generalized measurement in between. I'm aware of one paper that does that, but not much has been done. So you're right. You could have a kind of sequence of weak measurements, which would be more appropriate for some kind of open system evolution, and then you could phrase the whole thing. And I haven't seen any general kind of formalism of this type. I think this is a very interesting question.
Thank you.
Ian, I think you also had a question.
Yes, can you hear me?
Yes.
Okay. So two kind of minor points. The first is that I always interpreted Eddington's view on probabilities a little bit differently, in that what he was really saying was that, I mean, I think he saw that the quantum world was completely, well, was mostly reversible, and that it was the idea that because the quantum world was probabilistic, when you put a lot of probabilistic things together, it becomes irreversible. So, in other words, if you have, one coin on a table and you flip it, you have a 50% likelihood of getting the original state back. But if you have 10 coins and you flip them simultaneously, it's a lot harder to get that original state back, because it's when you keep getting random stuff on top of random stuff. So I think that's the way I always interpreted Eddington. The other minor point that I have always that's always kind of bugged me is that while theoretically quantum mechanics is fully reversible and time really doesn't have much of a meaning for it, and I agree with that point. I think time and space are emergent, but there are quantum processes that I certainly have never seen. So decay processes in nuclear physics, I've certainly never seen a polonium atom turn into a uranium atom. Yes. I think the 2 points that you are making are not disconnected, and probably Boltzmann again held most of these views because he had to defend himself against various objections, and I think lots of his answers kind of captured some of the points that you are raising. So I think the point that even though in principle you can reverse things, but that might be very difficult in practice, was, I think, one of those answers that was given to Logsschmidt by Boltzmann as well. He said, go ahead and reverse them, basically. That was the statement that he gave back. Or at least this is in the popular kind of culture, how it's told. So I think you're right. The other one, I think, is different. The point that I made was that somehow we tend to make the initial and the final
boundary conditions different in some sense. So it's almost like putting irreversibility into the whole game from the beginning. I mean, it does, you know, in many ways we are justified in doing that, like I said, because we tend to remember the past, and then that may not be an accident, although it's not sitting anywhere in our microscopic dynamics, this statement, but somehow we tend to have we're conditioning everything on our past knowledge, not on our future knowledge. But the fact that you can phrase quantum mechanics in this Aharonov way, where you give the initial and the final boundary condition, somehow shows you that this asymmetry is maybe not so fundamental. But I really cannot say anything more meaningful than just this.
So actually, I think I get it now. So what you're saying is that, so my example with the coins,
yes,
inherently sticks an asymmetry of time, yes, onto it, because the assumption that I'm reversing automatically introduces the concept of time.
Yes, I think that, and
okay,
to my knowledge, all of these resolutions and all of the arrows of time seem to me very similar and come from exactly this logic. But I'm not sure. I'm certainly not an expert on this.
Okay, gotcha. Thanks.
There's one last question from Chennai. Ravi?
Yeah. Can you hear me?
Hello?
Yeah, so, yeah, am I audible?
I think you should be slightly louder than that. I can just about hear you.
Okay. Yeah, so my question was, in this temporal entanglement, is there a notion of non-separability as in the case of spatial entanglement? Because, I mean, I can understand temporal correlations between two different measurements separated by time, but, I mean, entanglement sort of, there's no obvious analog of non-separability that I see here. I mean, I think you mentioned that in your lecture. But
yes, it's a very good point. You know, that's what I mentioned, that we somehow have this Schrödinger bias when we do quantum mechanics, because it is a more convenient formulation for many things. If you phrased Bell's inequalities in the Heisenberg way, even for spatially separated qubits, then I think the language would be much closer to temporal entanglement. And then you'd be talking about measurement outcomes being correlated in the quantum way, rather than starting by saying states are somehow entangled or disentangled. So in time, you're absolutely right. There is no notion of a state that stretches across time. So you can't really talk about separable and inseparable states as such. Although this is an interesting question, I don't know if this is intrinsically impossible, or maybe there is some clever way of writing it in an identical fashion. I don't know. I'm not sure if this answers your question either, but...
If there are no further questions, I would suggest to start with the second part of the talk now.
Okay. Do we know how to switch the camera back? Let's do it.
You can turn the laptop around and you'll just have to talk them through it.
How did he click? Yeah, he did something.
You need to click on screen share.
How to switch to the camera.
You need to click on screen share.
Yes, and how does that work? I think you did it last time, or someone did it last time. Screen. Is it enough to just click that?
Click it, and then it will choose a window.
Is that the one? So see if this works out, actually.
Yes, it does.
Good. Do I need to drag it a bit?
Yeah, it's okay. It's okay. I think it's fine.
Okay, so let me continue with the second part, which is, so the initial and the final correlations that we have are going to be very important in this formulation of thermodynamics. Let me again make a short story to motivate it before I do that. There's always a question of how to quantize thermodynamics. And many people would say that there are many approaches and that this is by far certainly not yet concluded. So what I mean by that is that you have to get analog expressions for standard thermodynamical quantities, but within quantum mechanics. And the question is, how does one do that? Of course, you'd like to come as close as possible to the original classical notions. And I think this derivation that I will show you now works the way it does precisely because it wants to preserve the classical entities that that exist in thermodynamics. So Jasinski's motivation, what he noticed is that there is a way of should I move
the light is too much on one side of the board, I think. It should be back to where it was.
Sorry about this delay. Okay, so basically, is it better? Slightly better.
It was too bright. Yeah.
So basically, what Jasinski noticed is that we always talk about the second law in a very general way, that we say here is an absolute upper bound to how well we can do work, how much work we can extract. But for a particular process, we are not really told how much less we do in general, and this is of course when we have an irreversible process. He noticed that if we phrase this differently, then we can actually get an equality out of this. And his way of phrasing this equality proved to be very robust. People have tested it in various classical systems, and then it was generalized to quantum mechanics, and it seems to hold under very general assumptions. I'm going to look at a very specific case because that's the one that relates to temporal entanglement. So the idea will be basically, if quantum entanglement exists in time as well, if I can have a high degree of correlations between two successive measurements in quantum mechanics than classically allowed, can I translate that into something useful for doing thermodynamical work? So can quantum thermodynamics be said to be more efficient than classical thermodynamics by exactly square root 2 or whatever is the discrepancy there? And it's interesting because in some sense the answer is yes, and that's what I want to show you. It's a very simple calculation. But in the other sense, if you construct exactly the equality that Jasinski started with, then you will preserve it even in quantum mechanics identically. And you can see where this simply comes from. It's not a big mystery. And it's all built out of these 2-point correlations. So let me tell you the scenario, and then basically I will explain it. So the usual way of phrasing the second law is to say that, so of course the most general statement is that the entropy of an isolated system can never really decrease, and in general it tends to its maximum value. If you take this isolated system to be a smaller system and its environment, then this really translates into, and now you're using this small system and you're using the environment to drive the system in some way, then under some circumstances, you can actually say that the amount of work that the system can get is at most bounded by, maybe I should write it slightly larger.
A bit larger, yeah.
A bit larger, yeah, thank you. So the amount of work that the system can do is bounded by the free energy difference between the initial and the final state during this process. So basically, I think here I don't really need this in some sense. What I mean here by work is that I'm allowed to go between the initial and the final state in any way I like. And this just says that no matter which way you decide to go between the two states, you can never exceed the free energy difference. So this would be the free energy at the end minus the free energy at the beginning. And this is almost like a definition of free energy. And I don't want to go into the details of which free energy, and under different conditions you will get different free energies, but basically this is the statement. And Jasinski said, well, if instead of looking at this, you actually exponentiate this work. So I will explain how this is done. And you don't look at the average work, but you look at the average of the exponential of this work. Beta is the usual inverse temperature. Then basically Jasinski noticed that this is the same as the free energy difference. And here I don't need the average because, like I said, free energy is a function of state only. And it doesn't matter how I move between the initial and the final state, I will get the same number. And the claim was that I think Jasinski proved it under more specific evolutions, but then people have extended it in all sorts of ways. And it seems that whichever way we extend this, we always seem to get an equality between these two. And let me just say how he phrased it, and I think you will see immediately where this comes from. So I'm going to assume, I'm going to look at a special case, obviously, because the special case will be the relevant one for temporal entanglement, and then you can see that the two are basically identical, the two scenarios. So in this case, I'm going to look at the system in some initial state, which I will call rho 0. I think it does. I'm not sure if this is the same as the notation in the couple of papers that you can download and read from, but it's something similar to what I have to say. So this is some initial thermal state, and it will be defined by the Hamiltonian of your system, and it will be defined basically simply as rho 0 is e to the minus beta h0 divided by z0. Z0 being the partition function, which is just a trace of this quantity here, and it's a usual normalization. So this is your Gibbs state initially. Now what you do at the first instance is you make a projective measurement in the basis of this Hamiltonian here. So it's very important to project onto the eigenstates of H0. I think I labeled this as something like E0n. N refers to the index of the nth eigenstate of this Hamiltonian, and 0 just means the initial Hamiltonian, if you like. So this is my first measurement. And that's where I'm going to make the connection with Bell's inequalities, because this measurement will then be, in my view, then done in two different bases. But let me talk about one single basis at the moment.
You're just requesting again that to keep the writing larger, just a little bit larger.
Okay. So basically, this is the eigenbasis of the original Hamiltonian. And what you do then is I will now allow the system to evolve in any general way. So this will be simplifying it, because in some of the notes that I put out there, I was looking at the general completely positive trace-preserving map. And I think you can phrase it like that and you will not lose anything from this equality. But for all our purposes now, it's sufficient to have an evolution which basically is just an exponential of some Hamiltonian. So it's like a sudden quench in some sense. You kick your system with this unitary transformation, and then you make a measurement. So it's completely immaterial how long you wait once you kick the system. The only requirement is that the final measurement is made in the basis of the final Hamiltonian, which I'm going to call E final sub m. So basically, of course, if you're talking about a qubit here, then I only have two eigenstates to start with, and I have the two eigenstates at the end of my evolution. So if you're already thinking and anticipating what I'm going to do to link this with temporal entanglement, this will be then a qubit, and you will be talking about two orthogonal states measured initially and measured finally. And then what Jasinski said is, or in fact this was Tasaki, so this was the quantized version of Jasinski. He said, now I have to define to you what I mean by this entity here, which is the energy, which is basically the work that I'm doing. and he chose to write it like this. So basically, e to the beta w is defined as the average is done with respect to probabilities n and m, and I will state exactly what this quantity is, and this is multiplied by the exponential. I hope this is visible still, of the energy difference. So this is 1 over kT n initial minus n final. So basically, if you take the energy difference between your projected value at the initial time minus the projected value at the final time, and you think of this as the work done in a particular instance of your experiment, then all you need to do is average with the probability for this sequence of outcomes to basically happen. And this is very, very easy. So basically, let me now define this P N M. So you start with state rho 0, which is the initial thermal state. Then you make a projection. I'm going to call these projections P sub N 0. So basically, in my notation, this is P0 sub N. Then I'm going to evolve the system with the unitary transformation specified here. And then I'm going to finally make a measurement in the final basis P sub M. And we know that the quantum mechanics, basically this is the slightly more complicated version of Born's rule. The trace of this entity here is the probability that a projected measurement onto the nth eigenstate will be followed by a projected measurement onto the nth eigenstate given the evolution in between. So this is this basic entity here. And now you can simplify this entity because your projection, final projection, is done in exactly the same basis as the unitary transformation. So you see, I sneakily chose this to be diagonal in the same basis, precisely so that I can commute these entities here. And then I can use the kind of cyclic property under the trace to cancel, because U times U dagger is identity. So basically, if you follow me, this goes here. In fact, under the cyclic property, and because P squared is equal to 1, I don't even need this entity here. Once I move this across, U times U dagger is identity, so these two go away as well. And somehow I'm left with a very simple looking formula, which ends up being nothing other than the probability to get nth eigenvalue out times the probability to get m if I got outcome n in the first instance. So you can see nicely how these probabilities conform to the usual Bayesian rule, that the joint probability for two outcomes is simply the probability that I had the first outcome times the probability that I had the second one given that I had the first one. So this here is nothing but the trace of Pn times rho. And this here is this quantity that I keep emphasizing is a symmetric quantity in time. It's just a product of the initial and the final projective measurements.
And someone wants to ask a question to you at this point.
Yeah. Jana, if you can read, is it going to be?
Can you hear me? Hello?
Yeah, just speak a little louder, maybe.
Okay, yeah. I'm just wondering, the shifting of the unitary with the final projection, that is only true if the unitary and the projection is with the same Hamiltonian, isn't it?
Yes, I think I deliberately chose this Hamiltonian to be the same as the measurement, or you can say I deliberately chose to measure in the basis of this instantaneous Hamiltonian. If you choose another Hamiltonian, then what I wrote down here won't look as nice as that. I mean, you can still phrase, like I said, you can still phrase Jasinski even if you choose a non-Hamiltonian evolution here, even if you do a completely positive evolution, you can phrase it then slightly differently, and you will get exactly the same result, but you won't get the same nice expression for the probability like the one that so you won't be able to commute in the same way that I did on the board.
Okay. Well, Jasinski still holds in all these general schemes, but what you want to say doesn't then, or it does?
Exactly. What I say that you can reduce the probability in this nice way will not hold if you have a general CP map here. So basically, the probability can still be written in exactly the same way. So the probability for a trajectory is the first measurement, then some kind of CP map which I will call phi. So this phi will now evolve the outcome of this measurement in the most general, completely positive trace-preserving way, or whatever you believe to be the most general evolution. But I think basically it only works for CP maps, I would imagine. And then I have P M final here. And the trace of this whole entity is still the same probability, but now you're absolutely right. In general, I won't be able to commute this projection around this phi and simplify it in the nice and usual way.
Mm-hmm.
What Jasinski would then do in a way is Jasinski could be phrased in the sense that you could be looking at the probabilities to go from n to m versus the probability to go from m to n, if you like, in the backwards direction. And then you can look at the ratio of these two probabilities, and you can use exactly the same formalism and get the usual answer. So I think it holds in the general case as well.
Okay, thanks.
Okay, so now let me basically apply this. So the statement is going to be the following now. Whichever you can see that in order to make analogy between basically in order to quantize Jasinski, I had to really phrase it in a very strict way that I do a projective measurement initially, and there is another complete projective measurement at the very end of the evolution. And this kind of gives me the notion of energy here, which otherwise I wouldn't really be able to define in any easy way. So this defines for me the energy, and then probabilities obviously are also defined, and I can define averages over different trajectories. And already the way I phrase this now, it's clear that this is going to be true no matter which projective measurements or no matter which unitary evolution I choose in my specific example. So I could start by having the state in the z basis, and I could perform the final measurement in the x basis, if you like, or z plus x basis, the conjugate in between basis, if you like. And for any combination of these, this will be identically true, simply by the logic that I wrote down here. So this is always true, no matter what measurements you make. And it's interesting then to ask yourself, how come there is a difference? So it would seem that Jasinski equality does not really discriminate between quantum and classical physics. There is nothing more that you can get in this formulation quantum mechanically than you could get classically. And what's interesting is what you have to do in order to reveal this is you really have to look at the individual moments of this work function here. So it's really all beautiful because each of the moments, I find it beautiful. Maybe it's a trivial statement, I don't know. In some sense, there is a certain triviality about it, but I probably won't be able to say too much about it this time around. But basically, if you zoom into different moments of this, so obviously you can write the exponential function you can write it as an expansion, and so that basically there will be something like sum of n from 0 to infinity, work divided by kt to the power of n divided by n factorial. So this is the usual representation, polynomial representation of your exponential function. And now you can say, okay, doing the average over this entity means I just have to add up all of these small averages over the individual work moments. So obviously there will be a trivial power, which is work to the power of 0. That's obviously not the interesting one. The first interesting one is just the average of work itself, which according to the formula that I wrote down is nothing other than the probability NM, the same one we had before, times En minus En. And then obviously the second moment is exactly the same average with power 2 and so on. So the nth moment of this, which is what we are calculating here, is this to the power of n. And so again, I don't want to go through all the details because we don't have the time. But the point I want to make is that this quantity here is effectively exactly the same 2-point correlation function that we used in temporal Bell's inequalities. So the only thing that's different is really your energy values, which are not necessarily plus and minus 1. And if you really want to make the full analogy, then you should choose your qubit values now, so that levels 1 and 2 can take values plus and minus e, and then you're effectively within the Bell scenario where the outcomes are plus and minus 1. So if you make your initial measurements in this kind of eigenbasis, and your final measurements also have the same values, eigenvalues for energy, then effectively each of these moments becomes a version of temporal Bell's inequality. And so now if you say, what if I run exactly the same thermodynamic scenario with 2 possible initial measurements, 2 possible final measurements, and then I construct the Bell-like average, then you can see that quantum mechanically this value will exceed any possible classical value. So the statement is interesting because each of these moments in its own way violates classicality, and you can get more work on average from each of these moments, but when you put them all together into the exponential, they all still add up to the free energy difference. And in my case, incidentally, I chose the same energy eigenvalues initially and finally, and the same temperature, which in fact makes this delta F equal to 0. It's the same free energy initially and finally, which means that this value is equal to 1 in this case. So each of the work moments is greater quantumly in the absolute sense than classically, but when you sum them all up, this completely disappears and you recover the usual classical result. So I thought this was, just check here, I think it's touching. Anyway, I thought this was very cute in the sense that it almost tells us, people ask this question, how come thermodynamics is still correct in quantum mechanics, and how come we didn't have to modify thermodynamics in the first and the second law once we realize that quantum mechanics is the right theory? And this, in a way, gives you some kind of answer that of course, the individual entities in this theory still have to be computed quantum mechanically, and they will show a variation, but certain other features, like the Jasinski equality, will be identically true, no matter what kind of microscopic description you have. The final note, which I want to just finish on, is basically going back to the question of reversibility, because you can see that so let me make this final statement. You can find all the details, incidentally, in the 2 papers that I put on the archive, so I don't want to really bore you with that. But the final statement I have is that this probability Pnm, and let me put an arrow now. So basically, I'm going from the nth eigenstate in the first projection to the mth eigenstate in the final. I'm just going to label them differently to show you that at T1 I do this measurement, and at T2 I do this measurement. I said this was equal to the probability to get n, followed by the probability to get m if I got n. what changes if you go in the back? So this probability is if I start from a thermal state, and here I do, this probability is simply your Gibbs-Boltzmann weight of the nth eigenstate in the thermal mixture. If you now ask yourself, what if I went backwards and I wanted to start from the final state, make an M measurement at T1, and then end up with another measurement at T2, the formula would be the same. It's just that you would be now asking for the probability for the nth eigenstate to start in, and then the conditional probability. So this is what quantum mechanics says is fully time symmetric. And I think this will be familiar to anyone who's ever derived the Born approximation, basically the Fermi's golden rule, if you like, when you're looking for the transition probability between two states. It doesn't matter whether you're going in the forward or the backward direction. What does make a difference is the prior. If you start from a different thermal state, finally, then these probabilities at the end could in fact be different from the initial probabilities. In my formulation, because I wanted to make them symmetric, these are the same partition functions. But in principle, you can have some initial Hamiltonian, you can have some final Hamiltonian. You can have a different temperature at the beginning and the end. And all that is going to contribute to an apparent irreversibility. Why going forward gives you a different probability to go backwards. And this is this point that I was making. It's actually put in by hand, by us asking for a different boundary condition on different temporal ends. Otherwise, quantum mechanics really does not see that. And that's kind of captured in these transition probabilities. I'm going to stop here and thank you all for listening. And obviously, I'm happy to answer as many questions as you might have.
Okay, thank you very much, Vlatko, for this nice talk. I would suggest we start with a question from Mauro in Belfast. And in the meantime, if others can think about questions, you can let me know in the chat. And also our stream viewers, we still have about 20 viewers at the moment. If you have questions, you can post them there, and we will pick them up and bring them in the live chat. Thank you.
Daniel, we have actually two questions if it's possible. Yes. So Tony had a question first, and then I'll have one.
Hello to all. I would like to ask a question about the first part of the talk about temporal entanglement. As far as I got the argument, in temporal entanglement scheme, the particle can be is entangled with itself at different times.
Yes.
Now, what about entanglement monogamy relations? I mean, you can see, you can either have a Bell state that's evolving, so the particle would be at the same time entangled with maximal space and time entanglement. Is there some monogamy relations space-time like? Thank you.
I think it's a great question. It's somewhat related. It's somewhat related to the question that Janet had at the beginning, namely, if you stick to projective measurements only, if you stick to one system and projective measurement, then you cannot have the three-party entanglement, for example, that GHZ state gives you. And the argument is simple, that a projective measurement erases any need for any information in the past. All that you need is basically the state that you projected onto, and that's all you need to calculate to get any future correlations. So basically, you can't have one of those states where you have a little bit of entanglement between 1 and 2. This would be, I guess, a W-type state. You have an entanglement between 1 and 2, and also between 2 and 3. Maybe not maximum, but lesser than maximum. If you only stick to temporal projective measurements, you can't do that, because the middle measurement basically erases any correlations between the initial and the final measurement. So any measurement you do in the middle of a quantum evolution kills any correlations with the past, and it says what matters is only the state which you project it to, basically. But I think this could be addressed by making weaker measurements, and then it would be really interesting to explore this kind of monogamy. How much can I be entangled between 1 and 2 instances versus 2 and 3 and so on? And I think it becomes even more beautiful if you involve spatial versus temporal entanglement. So you start with n qubits and you measure them at m different instances in time. And I don't think anyone has worked on these things.
Thank you.
Okay. The second question from Belfast is the following. So is again related to the first part of the talk, Vlatko. Hi, first of all.
Hi.
Hi. Is again related to the first part of the talk. And so you draw this comparison, this analogy with the Leggett and Garg argument. But as far as I can see, there is a big difference with respect to the original Leggett-Garg argument. And I'm not talking about the free evolution, it's the nature of the measurement that you perform,
yes.
which Leggett and Garg argument are non-invasive per se.
Indeed.
So could it be that the argument that you're making with respect to temporal entanglement is more related to a contextual sort of argument rather than a macro-realistic one?
Yes.
So and basically by excluding ab initio the non-invasive nature of the measurement that you're performing, you're basically enforcing the reversibility in your the reversibility of your process. Thanks.
I think it's a great point, Mauro, because that's why I wanted to stay clear of all of these assumptions about macro-realism and non-invasiveness. I must admit I don't really understand them myself. I'd much rather phrase it in the way that you phrased it, and I think then it becomes effectively what you're ruling out is very similar to what people do in consistent histories approach to quantum mechanics. So, you know, you're looking at a double slit experiment and you say, I've got a probability for the particle to go from here through one slit to the screen, and then I've got another history which is to go through the other slit to the screen. But I know that quantum mechanics goes beyond that. In a sense, there is a superposition of these histories that's also allowed quantum mechanically. And I think what my inequalities in some sense are showing is that you can't get away with these classical consistent histories. There is something beyond that in quantum mechanics. So I mean, probably the double slit experiment is the simplest one to. In fact, when we did this, I wasn't even aware of Leggett and Garg until the very last minute. I think Chaslav was the person who did his research properly as always, and I think he found these earlier papers. I really wanted to phrase it simply by saying, look, it's amazing that I can get the same violation, the same correlations in time on a single system that I can get from 2 qubits, and that was interesting enough to me.
Thank you very much.
Vlatko, perhaps you could answer the question from Jonathan Oppenheim that is in the chat.
Sure. Oh yes, this is a very good point. I covered this, so I could afford to be slightly kind of careless because there is this paper on the archive a couple of weeks ago of mine, and I think it's probably best to read about it there. But let me say what the question is, and then I will say that basically this is a good point, but it's not really fundamental. The point is the following: in Jasinski, you always make one initial measurement, and you always make one final measurement. Which is the same as the basis of the Hamiltonian in which you did the evolution. Whereas in the temporal entanglement, you have a choice of 2 different initial measurements, and then you have the choice between 2 final measurements. And this is absolutely right, that there will be a difference, which is why, in fact, for some of these moments in the work expansion that I was talking about, you will see the dependence on the initial state. So all the even moments, I think, will not have this problem, and their value will be independent no matter what initial state you start with, whether it's 0 temperature or infinite temperature. Whereas for the odd moments, you will see that there is a temperature dependence in your formula, and so this really is reflected in the formalism that you talk about. You can, again, you know, you can incorporate this into the Bell's inequalities by allowing two different non-trivial evolutions between the initial and the final time. So even this is somewhat related to what Janet was asking. You know, what kind of unitary evolution can I have in the
There are these papers by Ueda and Sagawa, and they are looking at the feedback situation. So in your scheme of things, I wonder how this would pan out. Simply, so basically, it's not just that you have an initial measurement and a final one, but you have an intermediate measurement according to which you might do something. And now I wonder how your temporal entanglement would basically.
I think, you know, it's also an excellent question. So I think the whole thing should be phrased, and that's what I did somehow, somewhat very briefly, again, because I was just lazy to write anything longer. But basically, I think you would have to phrase the whole thing more in terms of mutual information between the initial and the final measurement. This mutual information will have two components. One component will be the thermodynamical one involving the energy difference and the free energy difference. And the other component of mutual information will simply be the feedback that you are talking about, namely introducing more correlations between the initial and the final instant. And then I think I have a nicer formulation than I have a more general formulation than Jasinski, which actually takes into account the whole thing. But it becomes a statement about the mutual information between the past and the future, the exponential of it averaging exactly the same way as Jasinski. And you will get an equality as well.
Yes,
so I think we can do that.
Thank you.
Okay, sorry, during dropping out I lost if there's any other questions. If that's not the case, then let's all thank Vlatko again, and thank you for the great talk. Apart from a few technical hiccups, I think it went quite well. Thank you.